Today we're going to be talking about the quantum mechanical model and what we know about the current model of the atom, in particular the structure of the electrons in the energy levels. We just got done talking about Bohr and how he described electrons being in energy levels at fixed distances from the nucleus. He wasn't able to explain what was holding them at these energies, but just that they were able to transition between these energy levels, and that is again the explanation of the hydrogen line spectrum and all the other line spectra for all the other elements. So that really wasn't well received by the scientists at the time, other physicists, because there really wasn't any sort of explanation as to why electrons remained at these energy levels, just that they were. And so along came a scientist named de Broglie who helped to shed some light on how is it electrons could be living in these energy levels. And so Louis de Broglie came up with the idea of that the electrons must be traveling in like a wave-like pattern. He called this matter waves. And basically his idea came out of the fact that, we see photons really, which are, bursts of energy, and the fact that we know that electromagnetic radiation or energy is, traveling in this wave pattern. We can describe them as waves, but now there's this component of quantization, meaning that it comes in kind of like finite packets. So that, in that respect, it makes it kind of similar to the way we describe matter. And so de Broglie was then flipping the script and saying, well, energy can behave like matter in that it has finite amounts. Perhaps matter can also behave like energy and is actually traveling in waves, and that's why we see these certain amounts of energy. So as the electron moves around the nucleus, it does so with a certain wavelength, just like we see energy doing. And then he was able to demonstrate that there's a relationship between mass and wavelength, and here's the equation. So we have wavelength equals h divided by m times v. M times v, that's mass and velocity. H is that Planck's constant. And in terms of the derivation of that equation, you can look at the book, but it's not really as important to us for this topic. Now, this was a theory. As it turns out, it was confirmed through experimentation with X-rays and crystal diffraction that electrons do in fact travel in wave-like patterns, and so that was lent some credibility to this theory about electrons traveling in waves, and therefore that's why we can associate it with a certain amount of energy, just like we just talked about with the relationship between wavelength and other energy amounts. Okay, so here's a calculation that you could do to calculate the velocity of a neutron whose wavelength is 500 picometers. Mass of the neutron is 1.67 times 10 to the negative 27th kilograms. And so using that equation that we just looked at, be very careful about plugging in values. Again, picometers should be converted to meters for our wavelength, and then the velocity should come out in meters per second. I'm not going to do the calculation right this second, but and you can try that out, and I believe the answer to this one's in the book. Moving forward, okay, so if we compare the wavelength for an electron traveling at a speed of 1 times 10 to the 7th meters per second, with that for a ball with a mass of 0.1 kilogram traveling at 35 meters per second. So let's take a look at then, this idea of matter traveling in waves. Well, this actually extends not just to subatomic particles, but also to things that we can actually see. So that's why we're going to compare an electron versus a ball. So we're going to do the same calculation, and you'll check your answer in the pop-up question. But even something that's large travels at in this wave-like pattern. The difference is when you look at the wavelengths, that it's such a small wavelength in comparison to the size of the object that's why we don't ever detect that. But again, you'll check your answers, and then we'll move on. So pause the video, do the calculation, and then you'll check your answer. Okay, so we've got then, with describing electrons as traveling as waves, that then opens up a whole new discussion about well, how can we describe what the electron's doing? Where are they? And again, a wave, is not a straight line. So that electron, as it's, wiggling around in its wave-like pattern, there's more to be explored about, what do we know about then where the electron is and what it's doing. So another scientist named Heisenberg showed that the more precisely the momentum of a particle is known. So momentum, if you're not familiar with physics, is mass times velocity. He said the more certain we are about the momentum of a particle, the less precisely its position is known. And so this is kind of was a disturbing notion because we're trying to talk about what we know about electrons and trying to calculate where are they and what are they doing, and there's, because of how tiny the electrons are when we're looking at things that small, it's very difficult to with our level of precision that we're capable of, it's very difficult to know both the momentum and the position at the same time. So you get this equation, which again you can read about in the book where exactly this is all derived from. So delta x being uncertainty in position, delta mv being uncertainty in momentum, and h being Planck's constant again. So again, if we look at, like, if you were to crunch some numbers, I think there's a practice problem in the book and in one of the homeworks, but plugging into this equation, if we think about the hydrogen atom, the uncertainty in an electron's position is 1 times 10 to the -9th meters, and if the diameter of the atom is only 1 times 10 to the -10th meters, that means that we're so uncertain that our uncertainty exceeds the size of the atom itself. So again, for larger objects, it's kind of not really a big deal, but in wanting to pin down our understanding of the electron and where it is and what it's doing in the atom, this was sort of a groundbreaking idea that you couldn't know both of these factors about the electron. So if I can measure where it is, I can't tell how fast it's going. If I can tell how fast it's going, I haven't exactly pinpointed where it is. Okay, so quantum mechanics. So let's look at the quantum mechanical model. Again, we have de Broglie's idea of matter waves, and so in describing electrons as waves, well, we have ways to talk about the characteristics of waves: wavelength, frequency, speed. And so this guy Erwin Schrödinger developed mathematical equations where we could describe the electrons and their position. So these equations basically gave birth to quantum mechanics and how we describe where we can find electrons. The wave equation is designated with the Greek psi, so it kind of looks like this little wave, the trident kind of looking thing. So that's the wave equation designation. And when you square these equations, so we're not going to even see these equations, they're way more than we need to get into. If you square the wave equation, then what it gives you, if you were to plot it, is it gives you kind of a three-dimensional map of where the electron is likely to be found. So when we're talking about quantum mechanics, we're talking about probability of where am I likely to find the electron. So we'll be looking at these density maps, and the areas of higher density is where we're most likely or most probably going to find the electrons, and then as the density thins out, then we're less likely to find electrons in those regions. Okay, so we've got quantum numbers. We've already talked about the principal quantum number, which is designated as n, and we solve the wave equation. We get a set of functions which we're going to call orbitals, and again, we can correlate wave activity to energies. So that's the connection between the description of the electron in terms of waves and the fact that they've got a certain amount of energies in the atom. So we can, with our understanding of waves, we can translate that into an amount of energy. So each orbital then is describing the spatial distribution of the electron density around the nucleus in the atom. And there's 3 quantum numbers. Now, we're going to go over these, but these are not something we have to have memorized in terms of being able to assign quantum numbers. We do need to understand the concept of where these come from. We need to know the basic sublevel types that are within each principal energy level. We will talk about spin and all that stuff, but in terms of assigning quantum numbers, you don't need to be able to do that, but I will go over it just so we have seen it. Okay, so we've talked about the principal quantum number n, and that tells us the energy level. So that's kind of similar to what Bohr described. Values of n are integers greater than 1 and greater than 1. So 1 is closest to the nucleus, and again, as we get further from the nucleus, the quantum number increases. Then we've got our angular momentum quantum number, which is a L. The quantum number defines the shape of the orbital, and so again, these are all things that are derived out of those solving those wave equations. So where exactly these numbers are coming from, again, we're not getting into. So the allowed values of L are integers ranging from 0 to n minus 1. So if you look at the numbers that they give us down here, in the first energy level, n equals 1, it says that we have, an allowed value of L of 0, right? If n equals 1 and 1 minus 1 gives me 0. So I pretty much can only have the S in the first energy level, and then on up, we see that, we can have S and P, and then S and P and D and F if you do the number crunching. So the letter designations are more important to us, and so you should know these S, P, D, and F. And again, those are the orbital types, but this comes from the angular momentum quantum number. Okay, then we've got the magnetic quantum number, which is designated M with a little subscript L, and this describes the three-dimensional orientation of the orbital. So there's our values ranging from negative L to L. So if our value of L is 0, then obviously that goes to 0. If we have that's 1. If we go to our L value of 1, like in the second energy level, for the P, then that means we've got 3, right? So it'll be negative 1, 0, and 1 for our M values. And when you look at the table on the next slide, it'll make a little more sense what I'm talking about. So again, in any given energy level, there can be up to 1 S orbital, 3 P orbitals, 5 D, and 7 F orbitals if you were to look back at the numbers for M and then apply that to this equation above. Again, I'm not going to ask you to do that, but that's where this stuff's all coming from. There's the chart that kind of, I think, clears it up and lays it out for you. You can pause and look at that if you want. So again, orbitals with the same value of n form a shell or an energy level. And then if we have different orbital types within a shell, then we call those subshells. So, for example, in the second energy level, the 2s and the 2p form the energy level. And then, we would call the s orbitals, the 2s orbitals, that one subshell, and the 2p orbitals another subshell. Each of these orbitals, though, each of these types of subshells, notice, have a different number of orbitals. So this is what we've talked about in first year chem. S has 1 orbital, P has 3, D has 5, F has 7. And again, you can look back at the equations and kind of see where that comes from. All right, so what we should know is that S orbitals, again, those are always going to be filled in first in an energy level, and they have a spherical shape. And S, the radius of the S orbital increases with the value of n. S stands for single. Those are all things to note. So again, if we take the wave equations and plot them, what that gives us is graphs similar to this, and again, a 3D version like this, where we're looking at the probability of finding the electrons. So when we're looking at electrons in the 1s, we are most probably going to find electrons in this area distance from the nucleus. And then when we move out to each subsequent S sublevel, notice you get these nodes in these graphs. So this is an area of 0 probability. Again, this all has to do with solving the wave equation, where that comes from. But notice that there is a little bit of probability for the 2s electrons to actually be found in this section closer to the nucleus, but the majority of probability is out here. And then that area of highest probability keeps coming out further and further radius from the nucleus with each subsequent S sublevel. But notice there are always these nodes of 0 probability and then a section of lower probability in each of those. For the p orbitals, so again, by solving that wave equation, this is where we're getting this shape from. We know that the p orbitals have 2 lobes with a node in between them. So again, that node means there's 0 probability of finding the electron here. But if I am in this particular p orbital of this p sublevel, then I've got a probability of finding my electrons in either of these lobes. And notice there's 3 lobes for the p, so there's 3 orbitals for the p, and notice their orientation in space. So you may see them referred to as pz, px, and py, just indicating that they're on kind of the 3 different axes arranged. And so p stands for principal, something to note. Lastly, we've got, or not lastly, but we've got the d orbitals. So there's the L value for d is 2. So we've got 5 lobes, or sorry, 5 d orbitals. 4 of them have 4 lobes, and the other ones are kind of looks like a P with like a donut around it. As far as describing the shape of D, I wouldn't worry about that, but we just note there's 5 orbitals in the D, and D stands for diffuse. F I don't have a picture of, but F stands for fundamental. That has up to 7 orbitals in it. Other things we should note. So here's a graph depicting the energy of the orbitals for hydrogen. So what we know is that orbitals in the same energy level have the same energy. So notice we've got 1s down here, and we've got 2s and 2p, 3s, 3p, 3d. So when we have a very simple, if hydrogen has its electrons jumping in between the energy levels like we saw in that simulation, the electrons, again, are not, the energy level 2 or 3, all the orbitals that are possible have the same energy. What happens though, so the term for this is degenerate, so we should be familiar with that. So degenerate means equal energy for the orbitals. What happens though is as we add electrons, well, electrons we know are all similarly charged, and so that adds in this complication of repulsion between them. And so what we find is that as we add electrons, the orbitals which were in the second energy level, which were degenerate originally, are no longer degenerate once they start getting filled with electrons. So you'll notice there's a separation in energy where we've got 2s and 2p. They're close in energy, and we'll see that when we look at the PES plots. They're close in energy, but they're not degenerate anymore. All right, and then lastly, we've got the spin quantum number, and our next lab will take a look at this. And so it was discovered that 2 electrons in the same orbital don't have exactly the same energy. So although we looked at those 3 other quantum numbers, the principal quantum number, angular momentum quantum number, and the magnetic quantum number, we have this discovery that the spin on an electron can be different, and we can use a magnetic field to detect that difference, and that affects its energy. So again, in finding that electrons happen to be sharing the same orbital, they were not at the same energy, and so then there needed to be another way of describing the the fourth specific about where the electrons were and what they're doing. And so this is the spin quantum number MS. Notice it's different from the ML that we already talked about. Okay, so just like the planet rotates on an axis, electrons we kind of picture rotating as well. And so we use this, or we refer to these spins as either plus 1/2 or minus 1/2. Again, this all comes down to the wave equations. But basically, if 2 electrons are sharing the same orbital, they have to have a different spin, an opposite spin. And this is what's called the Pauli exclusion principle. So no 2 electrons have exactly the same energy. And so the exclusion meaning that, no 2 electrons in an atom have the same exact set of quantum numbers. That's the exclusion. And so again, we'll look at this in our lab and see if we can confirm that this is actually true. But the idea is that, again, energetically speaking, for 2 electrons to be in the same orbital, there's got to be something that allows them to be in that same space together, and that is that they have opposite spin. And so that's the Pauli exclusion principle. Okay, so that's where we're going to stop for today with the quantum mechanical model. We're going to look at electron configurations, orbital diagrams, and PES plots next. And again, we don't have to memorize assigning quantum numbers, but we should understand that each energy level, as it gets further and further from the nucleus, the electrons are at higher energy. The electrons can be in different shaped and sized orbitals, and the higher the energy level, the more complicated the energy levels get.